First of all, tidal forces are a rather complex matter to discuss. Top scientists in the field still disagree upon what actually causes these tidal bulges to occur twice a day on opposite sides of Earth. We are going to discuss the two most prominent explanations, one which focuses primarily on the centrifugal effect and gravity, the other which only focuses on differential gravity on Earth.
Alright, the first theory that we're going to talk about is mainly revolving around centrifugality into gravity, and I'm going to talk about centrifugality first. When an object, for example, the Earth, spins around on its axis, things will be pulled outwards, kind of. This is the same thing you see when a ballerina spins around, or you spin around. You'll feel that your limbs are being pulled outwards and you have to keep them in. This is the same thing that happens with the Earth, which creates bulges on the side of it. Now, along with the centrifugal effect, we have the moon pulling on the Earth from the right here. Now, when the moon pulls the Earth's center of gravity is technically moved towards the Earth. Towards the moon, sorry. Like this. So it's not in the direct middle of the Earth. This causes a stronger centrifugal effect on the far side of the Earth, which should cause a larger tidal bulge. Then on the other side, the moon's gravity is pulling the Earth, causing yet another stronger tidal bulge. And this creates similar tidal bulges on each side of the moon, on each side of the Earth.
In these other explanations, we ignore the centrifugal effect and focus solely on the differential gravity, which affects the Earth. Gravity works in a way where if a point is closer to the moon, I can try to draw the Earth actually, and this is Earth and this is the moon. A point closer to the moon will be more affected by gravity. It would be a more the force would be more powerful, which means that this point would be drawn more towards the moon than this point. This can be illustrated by smaller arrows, and this point would be even less pulled by the moon's gravity, or the gravity between the Earth and the moon. This means that the water on this side will be pulled away because it's closer to the moon. This will be pulled away from the seabed, creating a tidal bulge on this side of the moon. On this side of the moon, on the Earth, sorry, I'm mixing up Earth and the moon. But yeah, that would create a tidal bulge on Earth. On this side of Earth, we also have the water, but because this side the water would be further away from the moon than the seabed would be pulled away from the water, creating a tidal bulge. And this results in the Earth being squeezed in a way, so it gets the shape of an American football. So this is the crust of the Earth, and this is the tidal bulges, and then this is the moon. Okay, so one might wonder why the gravitational effect of the sun is not really significant to this, because the sun is so much larger than the moon, so you would assume that it would have an even larger gravitational effect and tidal forces than the moon. But because if you have Earth here and the moon here, then the sun would be so far away that the gravitational effects are restricted, and therefore doesn't really have a huge impact on Earth. However, it does have an effect upon the size of the tidal bulges created by the moon, because twice a month when the moon and the sun are in alignment. This would create the gravitational effects of the moon and the sun would add up, and this would create the highest high tides and the lowest low tides. So that means that we would have very large tidal bulges, which we call spring tides. When the moon and the sun is 90 degrees away from each other, the moon and the sun's gravitational effects they counteract each other, which creates what we call neap tides, which are the highest low tides and the lowest high tides. So this creates very small tidal bulges.
Alright, now we've talked about pulling and stretching. So we have the Earth here and the moon here, and we've talked about this point being pulled towards the moon and this point being pulled towards the moon and this one as well. But now we're going to talk about these points being pulled towards the moon. Now, when you look at a point being pulled towards the moon, you have to consider that this point is being pulled at the same speed because it's the same distance away from the moon. So it's being pulled with the same gravitational force. Because of that, and because of the gravitational effect on this point, which pulls it inwards, of course, it will actually look like this point is just completely moving inwards from your point of view. Now, this actually relates to a physical effect, so the water will be pushed inwards. And if you compare the pulling from this side and the pushing inwards on all sides of the Earth, it will actually look like this. And together, it will basically squeeze all the water down towards these sides, on both sides. Like this. And, whatever, yeah. Alright, a little fun fact is that Newton once stated with a quite complex equation that gravitational force is directly proportional to an object's mass, which would mean that because the Earth is so much larger than the moon, it would have a much larger gravitational effect on the moon. This would mean that the moon has tidal bulges just like the Earth does. And actually, we have looked up some of the facts, and the moon should have around twice the size tidal bulges compared to the Earth.